For 60 years, every attempt to replace silicon has failed. Graphene, carbon nanotubes, and dozens of other materials that were supposed to be the future. None of them made it. But now, for the first time, the semiconductor industry may have finally picked a successor. A few weeks ago, I was there when IMEC presented the new chip roadmap. And on it, something remarkable happens. Silicon starts disappearing. Not from your computer, but from the roadmap itself. And the material taking its place is just a few atoms thick. I'm a chip design engineer, and in this episode we will explore a new material that could replace silicon. The first microchip already running on it, and what it tells us about the future of computing. Subscribe to the channel and let me explain. For more than 60 years, the entire computing industry has been built on a single material – silicon. Every smartphone, every laptop, every AI chip. And yet, silicon was never supposed to make it this far. For decades, the semiconductor industry was obsessed with making transistors smaller. And every new generation unlocked cheaper and more powerful computing. But eventually, we ran into something we couldn't shrink away. Physics. As transistors approached atomic dimensions, strange quantum effects start to appear. Like quantum tunneling, when electrons behave like waves, which means they can pass through barriers they were never supposed to cross. They actually started leaking into places they were never meant to be. And at the same time, every new generation became far more expensive and far more difficult to manufacture. It looked like the dead end. Yet every time engineers found another trick. First, transistors stopped being flat and became FinFETs. Then we figured that we can wrap the gate all the way around the channel, giving us gate-all-around architecture. And honestly, the result is breathtaking. You're looking at Intel's first 18A transistor. Those tiny horizontal bars are called nanosheets, and they are the pathways where electrons flow. These are only a few dozens nanometers wide. And they're engineered to switch faster while leaking less current. But it's getting even crazier if you look underneath. Those darker lines are so-called power via. Instead of delivering power through the crowded top of the chip, Intel routes it from the backside. And this is two of the hardest problems in modern chip making solved in the same device. You would think that there isn't much room left for new ideas. But the industry wasn't done. Now we are building CFETs. An attempt to build two transistors in the space of one, literally stacking one transistor on top of another. And after that comes even more stacking. If you've seen my episode on China's new scaling law and chip folding, you will know exactly where this story is heading. Every generation bought silicon a little bit more time, but eventually every trick runs out. And a couple of weeks ago, I was there when IMEC presented it. A new chip roadmap all the way beyond 2040. This is a roadmap. The next decade looks familiar. 2 nanometer class chips today, then the industry moves towards A7, 7 angstrom class technology around 2033, which will be a remarkable milestone, the first commercial introduction of CFET. But then something strange happens. Around 2041, silicon starts disappearing. Not from your laptop, but from the transistor itself. Because after decades of shrinking transistors, if silicon can't be made any thinner, the only option is a material that already is. Imagine taking a crystal and peeling it apart until only a single atomic layer remains. That's the promise of 2D semiconductors. The leading candidate is a material called molybdenum disulfide. It's made from one layer of molybdenum atoms sandwiched between 2 layers of sulfur atoms. Just 3 atom layers in total. Now, before you ask, it isn't some exotic material. Molybdenum and sulfur are both relatively abundant elements. And the material itself is remarkable. It's just about half a nanometer thick. The semiconductor industry has spent decades trying to make silicon thinner. Molybdenum starts thin. That is its superpower. Because that gives engineers something they desperately want: control. And the thinner the channel, the easier it is for the transistor gate to control the flow of electrons. And better control means smaller and more efficient chips. Here, you're looking at some of the world's first advanced 2D transistors, built by TSMC, ASML, and IMEC, manufactured using EV lithography on a standard 300mm wafers. In other words, the world's leading chip makers have already started building the processes to make it real. And with every new prototype, the post-silicon era moves a little closer. Many people think this is just about making transistors smaller, but it's not. It's all about power. When the channel is only a few atoms thick, the transistor gains extraordinary control over the electrons flowing through it, and that means lower operating voltage. And in semiconductors, lower voltage is a huge deal. And for materials like molybdenum disulfide, we are targeting roughly half of operating voltage of modern devices, which could translate into dramatically lower power consumption. Based on the published papers, these transistors have consumed up to 1,000 times less energy than comparable silicon devices. And that is why this story is way bigger than transistor scaling. Right now, AI is pushing the industry into an energy crisis. Data centers are becoming some of the largest consumers of electricity on the planet. The industry doesn't just need more computing, it needs more computing per watt. And that's exactly where atomically thin semiconductors could make a huge difference. But the story doesn't end there, because replacing silicon might be not the end goal. Building on top of it might be. Next, we will look at the first working processor built on this technology, and for the first time see what a post-silicon computer might actually look like. But before that, recently I've been using the Anker's Prime charger, the world's most compact 160-watt multi-port charger. And that got me thinking, is the original charger always the best fit? When I travel, I'm carrying 2 laptops, a phone, an iPad, camera batteries, and other accessories. Normally, that means several chargers and a mass of cables in my bag. The Anker Prime 160-watt replaces all of that with a single charger. It has 3 USB-C ports, so I can charge multiple devices at the same time. And if I need to power something demanding like my MacBook Pro laptop, it can deliver up to 140 watts from a single port. What's interesting is how Anker manages to pack all that power in such a compact device. The key technology is based on GaN or gallium nitride. It wastes less energy as heat than traditional silicon. But what really matters is how Anker engineers it. With GaN Prime 2.0 and its MBUC architecture, Anker reduces inductor size to 1/4 of traditional designs. On top of that, Power IQ 5.0 intelligently balances power between connected devices, automatically reallocating unused wattage where it's needed most. And Active Shield 4.0 monitors temperature more than 10 million times per day to help prevent overheating. And the built-in display shows exactly how much power each connected device is drawing in real time. I travel a lot, and this one charger replaces for me a bag full of chargers. If you want to learn more, Anker is running Ask Me Anker Thing series. The link is below. But roadmaps are just plans. Building a working processor is something else entirely. And that's where the story gets interesting. For more than a decade, researchers were showing individual demonstrations, individual 2D transistors in labs. Always the question was obvious. Can you build a real computer with this material? And can it run Crysis? Now we have an answer. Have a look at this new chip from China. It's the world's most advanced processor built from a 2D semiconductor. The chip contains 6,000 transistors, each with a channel just 3 atoms thick, built from molybdenum disulfide. 6,000 transistors. Well, at the first glance, that sounds tiny and a bit disappointing, because a modern NVIDIA GPU like Rubin GPU contains over 300 billion transistors. But the legendary Intel's first microprocessor, the 4004, contained just 2,300 transistors. And unlike the 4004, whose transistors were measured in micrometers, the active material in this processor is only 3 atoms thick. But it's a real processor built around open source RISC-V architecture, so it can execute instructions, perform calculations, and run programs. For years, researchers showed individual transistors. Now they're showing a working processor. And that changes the conversation. Because getting one transistor to work, to switch on and off is difficult, but getting thousands of atomically thin transistors to work together is an entirely different challenge. When your semiconductor is only a few atoms thick, almost everything can go wrong. And yet, they reported a yield of 99%. In other words, almost every transistor worked, which brings us to the real challenge. For years, the question was, can these atomically thin transistors work at all? Now the question is changed. Can this be manufactured at scale? Because that's where most silicon challengers failed. The transistor existed, the manufacturing process didn't, but that may finally starting to change. One of the companies attracting a lot of attention in this space is C-Dimension. Their focus isn't the transistor, it's the material. How do you grow atomically thin sheets of molybdenum disulfide across an entire wafer at industrial scale? That turns out to be one of the hardest challenges standing between a lab and a mass-scale manufacturing. That may sound simple, but it isn't. Silicon has actually a 60-year head start. The industry knows how to grow enormous, nearly perfect silicon crystal ingots, slice them into wafers, and build billions of transistors on top. This process has been refined for years. But with 2D materials, we are starting from scratch. And molybdenum disulfide isn't a single element. It's a compound. Every molybdenum atom and every sulfur atom has to arrive in exactly the right place, at exactly the right time, across an entire wafer. Imagine painting a football field with a brush just one atom wide. That's the level of precision we are talking about. And then comes the real enemy, the grain boundaries. As the material grows, tiny crystals form independently. They expand outward, eventually they collide and defects appear. Think of a frozen lake. Ice forms in different directions, and where those patches meet, cracks appear. In the semiconductor, those weak points become defects. And for decades, silicon manufacturers learned how to eliminate them. 2D materials haven't. And that's exactly where many promising technologies have failed before. Not because the transistor didn't work, because the manufacturing never did. And C-Dimension believes it has a solution. And the basic idea is quite elegant. You flow gases containing molybdenum and sulfur across a silicon wafer. The atoms react on the surface and slowly assemble into a crystal only a few atoms thick. And the challenge here is the temperature, because traditional methods require temperatures close to 1000 degrees Celsius, hot enough to destroy the transistors already sitting underneath. C-Dimension claims it can do the same thing at around 200 degrees, low enough that the silicon underneath survives. Which opens the door to something much bigger. Because replacing silicon might be not the most interesting outcome, building on top of it might be. Now, for the first time, we are touching the idea of true monolithic 3D computing. You build a layer of silicon transistors, then a layer of 2D transistors on top, then another and another, like constructing a skyscraper, with entire logic layers stacked vertically. And if you watched my previous episode about Chinese logic folding breakthrough, you're about to have an aha moment, because these are not two separate stories. It's two different attempts to solve exactly the same problem. For decades, the semiconductor industry improved chips by shrinking transistors. And eventually it started running out of room. So the industry began moving upward. The first step is CFET, two transistors stacked on top of each other. Think of it as adding another floor to the transistor. The second step is what companies like Huawei and IMEC and TSMC are exploring by stacking logic using hybrid bonding. Instead of stacking transistors, you manufacture multiple silicon layers separately and then connect them with millions of tiny vertical links. That's what made Huawei's result so interesting. But monolithic 3D goes one step further. Instead of building two separate logic dies and stacking them together, you build the transistor layers directly on top of each other from the beginning, layer by layer inside a single chip. Basically, you have no bonding interface, just one monolithic 3D chip. If CFET adds another floor to the transistor and logic folding adds another floor to the chip, in monolithic 3D approach we are building the entire skyscraper tower with shorter connections and far less energy wasted moving data around. That's why Intel, TSMC, and the entire chip industry watching it so closely. Not because this material is better than silicon, but because this is a potential path forward when traditional scaling finally runs out of road. And that's why so many researchers see it as the end game. And this race is bigger than a single material. Today, a lot of attention goes to molybdenum disulfide, but it isn't a single 2D material. It isn't running alone. Research labs, including IMEC, are also looking into materials such as tungsten disulfide and tungsten diselenide. Think of them as members of the same family. Each has slightly different electrical properties. Some are better at carrying electrons. Others are better at carrying the positive charge, but modern chips need both. So the future may not belong to a single material, but to a family of atomically thin materials working together. If we look 15 years ahead, the first 2D semiconductors probably won't appear inside the CPU or GPU of your next laptop. New technology rarely arrives right at the top. Usually it earns its place step by step. The first commercial applications will be likely much smaller, like RF switches for future 6G networks, photonics, or MEMS devices, because these applications are easier proving grounds and they don't need billions of perfect transistors. They can benefit from the material much earlier. That is how many new technologies enter the market. First in specialized applications, and only later at the heart of mainstream computing. It may sound slow, but the history suggests otherwise. Every new breakthrough in semiconductors looked immature at first. Silicon photonics, superfins, EUV lithography, all of them spent years in what engineers call the valley of death. And yet, we eventually made them work. And that's why I find this moment so fascinating, because we are witnessing the first steps into the post-silicon era, the moment the industry is seriously preparing for the life after silicon. If you enjoyed this episode, share it with your friend, and now watch this one where I explain a disruptive technology which will allow us to shrink an AI data center to the size of a shoebox. Or this one where I explain Chinese logic folding and a new tau scaling law, and why the future of computing is vertical. Love you guys, and I'm gonna see you there. Ciao.